Today's topic is network programming. We're getting to the end of our things we have to learn about Java. Well, let's see. The goal of network programming is to get two machines in different spatial locations connected by the network, a network, to talk to each other. And I guess I want to start out talking a little bit about the internet. Probably everybody in the world has been bombarded with stuff about the internet the last 5 years or decades, but I want to kind of back up and give you some overview of the technology and what's going on under the covers, because some of it you have to be aware of. So when you look at a typical network application, not the part that you write, but the part that's going on hidden from you, there is a whole stack of software going on. A lot of times you will see these layer cake drawings of various software layers. And what these mean is that there is kind of one conceptual abstraction down here, which has an interface layer. Okay, this is some interface in the kind of large interface sense. And then built on top of that and calling into that is yet another layer of software imposing yet another abstraction with other functionality, additional functionality, and then that gives you an interface at a higher level. And then on top of that, writing to that interface, there's another layer of software which gives you another interface, and this thing just you build big layer cakes of these things. This is enormously common, strange phrase, very common software organization. And if you work professionally in this, you will see scads of these. And your job will either be to build software up from some layer, using one of these layers of abstraction, or build the whole thing, or just use a stack. The layer that we will probably be using, or you will be using for your project, is this layer down. And but let me start with the bottom up. The bottom layer in the standard network stack is the transport layer. If you really get into networking and you study the network standards ISO book, there's actually 7 layers in this layer cake. So I'm kind of, if I leave out some of the 7 layers, don't get upset. But these are the ones you really need to keep in mind. The transport layer is the lowest level of thing that's going on. That is the electronics and the hardware and the underlying protocol that's moving bits physically from one machine over some wire to another machine that's connected to it by a wire. So it's the most direct level of connection. And there's the typical technologies are Ethernet cards, which will run through a physical wire, or in your case, you have a Ethernet probably running over a wireless network.
More or less.
More or less.
Running is a strong word.
Right. There's other transport protocols that will work over serial lines, so you can tap into the internet from dial-up modems. There's PPP, which stands for point-to-point protocol. There's something called SLIP, which is another serial line or modem type internet connection. There's other things besides Ethernet. There used to be a huge divergence of things aside from Ethernet, but Ethernet has grown and conquered, at least in a lot of sort of office-type integration environments, or even home now. You can get a nice home Ethernet set up pretty easily. So all this does is move data from one machine to another, and the data is organized into units that are essentially defined by the hardware protocol. So it's going to send a chunk of data at a time and ship it to the other side. On top of that, we have our friend IP for Internet Protocol. Okay, this is a protocol. A protocol is a conversational system between two machines that let them exchange messages and communicate. Okay, it's a language for two machines to speak to each other over the network, over a network. It basically involves machine 1 sending a message to machine 2 reading that and sending one back, or machine 2 expecting one and not getting it and sending a message back. So the job of Internet Protocol is essentially packet routing. Okay, Internet Protocol is the thing that makes the Internet, and it imposes a address space on all the machines in the world, known as IP addresses. And at the moment, the current version of this, which is IPv4, I believe, the addresses consist of four 8-bit units, 4 bytes, which are usually written as dotted pairs. So let's see, I believe our internal IP addresses are all 10.11.4 and then some other number. So this is, I believe, one of the TA machines, the IP address for one of the TA machines. This is just 4 bytes. So each one of these numbers can vary from between 0 and 255. And they're just usually written with dots. So the goal is that each one of these 4-byte numbers uniquely identifies a machine on the Internet. Okay, and if you do the math, you get about 2 billion possible machines, and we're probably running out of these just because of the way that things are clustered. So one of the jobs of the IP protocol, is to take a message from any machine in the network, okay, and you add into this message a source address, which is you, and a destination address, which is where you want to send it. And that destination address can be on some machine halfway across the world. And the job of IP and all of the technology in between which sorts IP is to make sure your packet gets there, or at least try to make sure your packet gets there. So using the transport layer, it basically gets sent in a series of hops. Okay, there is a network of routing that makes IP work. So even though your machine, okay, this machine might not know where some foreign machine, say 140.16.0.1 is, okay, it might know exactly where to send it if this is on your local net. On the other hand, if it's not, it sends it to its routing machine. It has a rule that says if I don't know where to send something, send it here, okay, some machine on your local network. That machine has to be connected to some other machine which knows more about where to send things. So basically things get routed from machine to machine, bounced from machine to machine across the network, and eventually it'll end up here. Okay? Usually the routing is done hierarchically so that this is kind of the most important place, and then this, and then this. So it first kind of routes up to find where this part is, and then back down. But it doesn't have to. One thing about the current Internet routing is, at least at the low levels, at the lower parts of the tree, it's hardwired. So it's not dynamically routing. If your routing machine or some part goes out, you lose connectivity. At the higher levels, there's probably fancy technology to switch over and fail over. But your machine probably has a single point where it's sending all of its messages to get them started. But that's basically the job of IP. It sends these things called IP packets, and they have a number of pieces of information in them: a source address, a destination address, probably some idea of timeout, and then some fixed small amount of data. All right, so you basically send these, and because it's going through a variety of these hardware protocols, sometimes this data has to be broken up into several small packets to make it through this protocol, but then they're reassembled and shot over. IP makes no guarantees other than it's going to try and route your packet. Okay, it gives you no information as to whether your packet got there. It if you send a bunch of packets out, some of them might get there, some of them might not get there, and there's no guarantee in what order they're going to get there. Okay, but it does give you this namespace and routing capabilities, okay, which sometimes is all you need. It might give you order guarantees, I'm not sure, come to think of it. The next layer, there's a lot of protocols built on top of IP that take advantage of this naming scheme and routing scheme, and that basically gives us the current internet as we know and love it. The most useful protocol that we'll see, the one that we'll use the most, is called TCP, for Transmission Control Protocol, I believe. There's other ones called UDP. Do you know what UDP stands for? I think it's Unreliable Delivery Protocol, but I could be wrong. And there's a handful more on top of that. TCP, the abstraction that maintains on top of IP is the notion of a connection and a stream. It basically maintains and implements a stream protocol over the network for you. So it lets you make a connection to some machine at some foreign address and gives you stream semantics on that connection so that you can do reads of random numbers of bytes from the connection or do writes on random number of bytes in that connection. Yes?
Sorry, but presumably these streams could get interrupted at any stage because you may have to wait, a millisecond or 10 seconds for the next packet of data or something.
Oh yes, and that's why the reads on the network can be blocking, and even the writes on the network can be blocking. Okay, but you do have the basic stream semantics, which has all sorts of nice guarantees that the data you send out is going to arrive reliably at the far end, and it's going to arrive in the order in which you send it. Okay, so TCP is something that essentially makes a network connection look like a file connection or our console connection. We've got nice stream semantics. Because you're operating over the network, its feel is going to be kind of different. Its reads are probably you're going to be blocking more on reads than you are, say, reading from a file, because the data is coming in unevenly from another source, a foreign source, and the network could be slow or fast, or there could be hiccups. Similarly, when you write, you don't often get blocking writes when you write to the terminal or when you write to a file. But networks you can get blocking writes to because, again, we have this pipe metaphor, and this pipe can only hold so much stuff in it until somebody has to take stuff off the other side. And so if you are feeding stuff in at very high rates and somebody's taking out at slow rates, eventually everything will back up and your writes will start blocking, and you won't be able to stick anything more into the pipe until somebody reads something into it. What else to say about that? Again, in contrast to writing to a file, a stream on a file, or a stream on a terminal, these are a little bit more fragile because there's a lot of technology getting your packets to some machine on the internet. So it can happen that the whole process will break down, that the communication path will break down, the foreign machine will crash, or one of the intermediate machines will crash. And so this stream connection can just break, okay? And you'll get some exception back from the stream that says it's broken, and you'll have to deal with that. You don't often get that from a file or the terminal, but it's one of the things you have to compensate for. On top of TCP then, once we have this reliable stream protocol, okay, there's all sorts of application protocols built on top of this. And application protocols are, again, a type of conversation between different programs, and in this case they're at a higher level and they're geared towards some particular application. There's a bunch that run on top of TCP. There's a bunch that run on top of UDP. UDP is a more packet-driven protocol. You send, rather than stream semantics, is packet semantics, and it has less guarantees in terms of reliability and the like. But on the other hand, it takes less technology and is a little more lightweight than TCP. So a lot of the kind of internet telephony and some of the streaming probably uses, the internet telephony definitely uses UDP. Some of the streaming may use UDP as well because it's more lightweight and you're doing less work. So it's running a little faster at the cost of a certain amount of unreliability if the network, has problems.
If you didn't have the stream connection layer at all,
Yeah.
then you would still get data, but it would just be all over the place? Or?
Programming in IP is difficult. Yes, you essentially get a sequence of packets out of IP. Okay, and you know the source from which they came, and you get some data. And that's pretty much it. There's some other header fields there. Okay, so what TCP does is it, takes your IP packet and then adds some more TCP header information on the packet that organizes it in terms of connections and streams and which packet this is in the order and whether you lost any and that sort of thing. And builds in timeouts and buffer sizes and all the stuff to make it work. So yes, you can program on top of IP directly, but it is not a happy thing.
So is it the TCP that sends a request to the sender for new packets if it detects missing packets?
Yes, it does. Well, I think both at various layers will do it, but mainly TCP is going to do retries. Yeah, no, I'm getting fuzzy in my old age as to which one of those does which one of them has sequence numbers. But I believe it is all in the TCP. But don't hold me to that. One other thing I want to say about IP addresses is there's a magic one, which is often useful to know. 127.0.0.1 is a magic one call that refers to yourself. Okay, so this one, no matter what machine that you are running it on and connecting to, is always going to just loop back and talk to yourself. So it's a good way to debug your network code, is just loop back and connect to yourself. Okay, network stacks. How do we, since I said we were going to operate at the TCP level, the major programming abstraction for operating at the TCP level is called sockets. This metaphor is pretty uniform now across the programming community. Pretty much every system I can think of that you would be programming in would give you a sockets layer to run TCP and sometimes even UDP connections over. I believe it originated from some work at Berkeley on Unix, but has since been propagated. So there's a Windows implementation and for other machines. And a socket is essentially think of it as just a TCP connection, or in some case, a UDP connection to a remote machine that's giving you these stream semantics. Unlike the case in the streaming I/O, where Java gives you a great deal of complexity, and is much harder to do than, say, in a C, C++ environment, in the network space, it's just much easier. They have hidden all the ugly stuff and given you exactly the 3 or 4 things that you need to do what you want to do. So the network programming in Java is much more of a pleasure. Sockets now in Java are going to be objects, which are of class socket. And to make one of these guys, you just call the constructor new socket. And 2 arguments, host name and port. Okay. Host name can either be one of these guys as either a string in that format, or Java will give you, there's an object we'll talk about later that represents internet addresses. Or you can use a host name, like www.arsdigited.com. On top of the IP naming scheme, and somewhat different from it, there is this domain naming scheme where you get to use text strings to name machines or destinations. And that is maintained by a different set of protocols and a different set of machines on the network, okay, all of which running on top of IP underneath. But its job is to take one of these strings, like arsdigited.com, and turn it into an IP address for you. And so this is the DNS system. And so the first thing, if you were programming this at the very lowest level and somebody gave you a name like arsdigited.com, you'd first have to use DNS to look it up and translate it into an IP address, and then you'd have to open a socket on the IP address. And Java nicely does all that for you. Okay, so this command, where this is a string and that's an integer, does about a page worth of C code for you, of rather obscure C code. So very, very nice. A word about the port. The port is another notion connected by or imposed by this protocol layer. Is when you talk to a machine, you would like to talk to a specific application. On a given foreign machine, there could be dozens of programs running, okay? And you not only have to say, I want to talk to this machine, you have to say, I want to talk to this program on this machine, okay? And the way you select essentially which program you want to talk to are these port numbers, all right? And these are just integers. Usually they're small integers, but they can be larger integers. And essentially, two machines across the network have to agree if they want to communicate on some program, have to agree to talk to each other and listen, request and listen for connections on a given port. So every application you can think of, in order for me to talk to, say, a web server on a foreign machine, I not only have to know what the internet address is, I have to know what port it's listening on. Now, fortunately, most standard programs, network programs that you use, have standard ports, so you don't have to know, which one it's running on each machine. And if you remember that HTTP URL syntax, it's hostname : port. Okay. It lets you explicitly specify the port if you happen to know that some web server is running on a non-standard port.
Each port can handle multiple threads.
Right. When we talk about server side, this is, if you're a client, how you would do a connection. The metaphor for most of these TCP programs is that you have a client and you have a server, hence the term client-server architecture. And the server, for any given program, is listening on a port. So web servers typically listen on port 80. All right? Clients, when they want to connect to a web server, do this connection to the port. So this guy would do make a socket on machine, call it foo.com, comma 80, and that would make a connection and start a communication here. So what really this is going to do is, as soon as it gets this connection, it's kind of going to take the end of this guy and make another connection here, we'll see, and start talking over this. And now this guy is going to be free, the port 80 is going to be free to accept more sockets. So every time somebody makes a request here, this end of the connection gets bound to some other, it creates a new socket and binds it and ships it back. So this guy's always listening on a given port. So if you're a client and want to connect to any machine at any port, you just make one of these. You just do this, and it gives you a new socket. Some dangers here. This is a constructor, and like constructors on like our file input stream, lots of things can go wrong. Okay, some of the things being this host name could be bogus, that there's no machine that the DNS server can translate that to. So that's one thing. The IP address that you try, and it could have a legitimate IP address, but the foreign machine could be down or unreachable or too busy to talk to you. Most of those are going to be indistinguishable because your attempt to connect will simply time out. Or if it's almost too busy to talk to you, it probably has enough CPU to send you a rejection and say, I am here, but I'm not going to accept your connection. That's another possible response from this thing. So there's lots of things can go wrong, which means we have to wrap it in a Exactly. So you wrap all these guys into try block, have catch handlers for all the things that can go wrong. If you're lucky, the thing will connect. Once it connects, you're ready to rock, really. You can get this thing will have this thing has a get input stream and get output stream methods. Okay, and these, once you have a socket, you can get the input stream and output stream methods and then start gluing up those chains of stream things that whatever you want to use. For example, if you want to send text, you would build some kind of buffered reader and buffered writer on top of these things. If you wanted to send binary data, you'd probably put a buffered input stream and a data input stream on top of it, or a data output stream on top of it. So you just, once you've got one of these things, you just treat it like you've got it from file open stream and build up the normal set of connections, and then use the normal stream read and write stuff, or println, or whatever you like, to run on streams to work on these. So that basically everything you learned on how to do file I/O ports nicely over to network I/O. The only thing new is to make the connection, you have to do this, and then get your input and output stream.
Why do you say this port is like a program? It looks more like it's like a pipe.
Well, the port is just a number. It's a special number in that everybody kind of has agreed on this number. So what is going on in our server machine is that there is a program. Let me draw it in. Say we're using Apache web server. So we have Apache running here on this machine. And what Apache is doing is listening on this socket for connections. Okay, so port 80 has a web server listening for connections, and as soon as some client connects, it's going to make one of these sockets, and that kind of will propagate back, and then this will succeed. And you're ready to talk to do the actual communication protocol. Yeah.
I know, like, one of the things that people do is they probe your ports. What are they waiting for? Or looking for?
Oh, well, you basically, you can write a program that cycles through all those port numbers on your machine, okay? And you just increment through them and see if this call succeeds on any of them. Okay, if it succeeds on any of them, that means you have a stream in which you can talk into some program, right? In general, you might not know what program it is, but, then you can try, once you've got a connection into that machine, you can try and do stuff. Okay? And well, let's talk about what kinds of, let's talk about protocols for a sec, yeah?
Well, all of these, this might be leading into what you're just about to go into. These, since you have two autonomous things, every time one guy writes, the other guy has to be ready to read on this stream, right? And so they have to know something about.
It's not quite that tightly synchronized in that both the TCP layer and hopefully the IO stream layer on both sides is going to provide some buffering. So when you're writing, you probably want to use a buffered writer and a buffered reader. The guy on the other side will. And the TCP protocol will provide some limited set of buffering. And if not, it'll block so that if you're trying to write, you'll just sit there trying to shove data in until somebody pulls something out, in which case it'll succeed. So, so now we know how to open a connection on a random port, and we know how to send data and read data just using these read and writes. So now all we have to do is figure out how to do something intelligent over that connection. And that's where, again, cooperation comes in. And cooperation over the network is in form of protocols. Network protocols are essentially the network equivalent, the network communication equivalent of what maybe interfaces are in the larger sense to modules that are communicating by method calls, okay? If you have, say, a library you want to use, the way you would specify that library is to give the list of method calls that you can make into this library, what they're going to do, and what they're going to return, all right? Now, in most of these protocols, you are not running something similar to a method call, but nonetheless, you want to do the same sort of thing that you want to provide a network service, you're a server, so you want to say, okay, I'm going to provide this sort of service to you, and the way you get access to these services is you send me this message and I'll send you this data back. You send me this request, I'll answer that. So it's not really a procedure call, but there is this conversation that goes back and forth that's agreed upon like a procedure or method-based interface that will tell you how to do all the capabilities you can do. And these things run under the notion of application protocols, and there's a lot of them. And problem set 3 will have you writing one or implementing one. You don't have to design it. Some of the favorite ones are HTTP, which is the web protocol. There is FTP, which is a file transfer protocol. SNTP, SMTP is one of the mail transfer protocols, right? There's a protocol for Telnet for remote connecting into a machine. There's a protocol for Finger, which will give you information about who's logged into a machine. There's a protocol for Ping, which just tells you whether the machine is up. Let's see, what other? There's NNTP, which is the protocol for net news. No, I think NNTP is TCP, yeah. And to give you a flavor of how these work, I've given you in the notes a clip of a sample NNTP protocol transaction, actually a number of different transactions, so you can see what goes back and forth across the network. NNTP is a text-based protocol. Text-based protocols are nice for debugging because you can debug them with Telnet, and you can look at the messages that you send and send back, and you can actually read them. A lot of protocols are binary protocols that you send, the protocol description will give you some map of a packet that you're supposed to send and tell you, bits 0 through 8 have this data, bits 8 through 16, or maybe bytes 0 through 8, and you have to basically make something, data structure that looks like this and ship it out in binary form. They're more concise, but they're more difficult to debug. I think the Gnutella protocol, which you're going to implement, has a little of each, so fun for all. So if you just look at this protocol, it's the S is what the server sends, and the C is what the client does. And it starts out with the server listening on a port. And each one of these applications I talked about has a standard port associated with it. So when you want to talk to some service on a machine, you can guess at where it's going to be running, or most likely. And the port for NetNews is 119. So if you want to connect to any NNTP server, you would try and make a socket to one of these on port 19. And when a port, so the server's listening on that port. We'll talk about how to do that in Java in a sec. The client connects, and then the server acknowledges that the client has connected and things are up by sending a message. And it just sends that 200, my name, new server ready stuff.
So what's the 200?
200, a lot of these text-based protocols start out each reply with a message, an error code. Okay, so it tells you whether things succeeded, or if it didn't succeed, what kind of error there was. 200 is success, I believe, in the 200 series are various types of successes in NNTP. I think 200 series is also success in HTTP. Does anyone know? Does anybody remember? I think it is, yeah. And like the 400 series is file not found, and the 500 series of errors is illegal operation on server. And then there's some 300s and 100s.
So if we tried to make a NetNews connection to some server that didn't have NetNews,
well, then this would not succeed, okay, because there'd be nothing listening on that port. Okay. Or, indeed, if there was something listening on that port and it wasn't NetNews, then you'd get some, you'd probably get some random reply back. Okay, so basically, if you're the client, you're going to connect and you're going to listen for that first 200 something new server ready to ensure that what you talk to really is a net server, a NetNews server.
But does it have to say like news server ready there? Can you just say 200?
I believe that the protocol will specify which parts of that line are required and which parts. This is just an example, and there's a protocol spec that will tell you exactly what's required and exactly what's optional. Okay, and then as you go on, it's a series of transactions where the client sends a command word in text and then a carriage return, and then the server sends data back, and then the client sends another command, server sends, And if you've ever written, say, something to connect to NetNews, you have to do a number of these transactions just to get started. You have to get the list of news groups and send which news groups you're interested in, and then get the headers. And, so there's a lot of back and forth going on behind the user interface that you see. Let's see. Going back to your question, the fact that there's all of these standard things running on ports gives people an opportunity for mischief, depending on how secure people have made their server machines. There's Telnet, which runs on port 25. There's Finger, which I think runs on port 23 or 21. So there's all these ports with these standard services on them that anyone on the network connecting to one of these machines has a reasonable opportunity to expect. So unless you've secured your machine, anybody could attach to port 25 on your machine, open a socket. The machine will respond if it's running Telnet server, and unless you've told it not to, probably it started when up on boot. And now people have this connection to Telnet into your machine. The next problem is how to log in, but that's just a matter of password guessing. And Finger, anybody can connect and ask for who's logged in, or is this person logged in. So there's probably somewhere between a half dozen and a dozen of these things that typically come up on boot, if in default configurations of servers that are just there listening on ports for connections that anybody can connect to. Just as a side note,
well, finish your side.
I was going to say, one of the standard attacks on these is to take advantage of sloppy implementation of the server. Okay? Most of these holes have been closed by now, but one of the early set of holes was you could connect to one of these servers and send a message that's bigger than the message expected by the protocol. And sloppy implementations will take that overrun and do something bad with it, so and let you gain control of the machine. Most of these, as I say, most of these bugs have been patched, but that is a warning against sloppy programming and a argument for bounds checking on arrays. Okay, if you don't have bounds checking on your arrays, and somebody, you let some outside program write into one of these arrays, the data at the end of that array is going to be vulnerable. Okay, so just as good practice. Java does not let you do this, but other languages certainly do let you write into arrays without bounds checking. So, in your notes, there is a short program. Yes. Oh,
I was going to ask. I don't really know much about firewalls, but it seems like aren't firewalls going to maybe block input to one of these ports or something like that?
Yes. One thing firewalls will do is, they restrict connections to the number of ports, certainly, and they.
Do we need to know anything about firewalls when we're setting up these sockets, or is that just automatic?
No, I think that our sockets at this layer, I'm not sure, I don't think need to know about firewalls, okay? If there's a firewall that's preventing this, it's just going to fail. Okay, what you might have to know about is proxy servers, okay? And a proxy server is something that is sitting on your firewall that's going to let some subset of, kind of get you around the firewall in some, for some subset of connections. And that means you have to, instead of talking directly to the port, you're really talking to the firewall, telling it you want to talk to the port. So there's some added complexity in that, and the book goes into that a little bit. We are not connected to via a firewall, I believe, so I think we can just go out and ravage.
The only trick is we don't have assigned DNS numbers.
That's true.
So I know what you're doing.
That's true. Kind of a detail that's a little bit, but not really relevant to the project. Going back to how IP numbers are assigned, nothing to do with Java programming, but how IP numbers are assigned. There's two ways they can be assigned statically by your network administrator. He can just go to each machine and lock down an IP address, which is good in that the IP address is stable over time. But if you have a network that people want to add machines to dynamically, like if you want to bring in your laptop and plug it into the network and have it work, that's not very satisfactory because your laptop won't have an IP address on a strange network. So there's yet another protocol called DHCP, which allows you to dynamically distribute IP addresses on a subnet. So, and that's what this system runs here. So when you plug in a new machine or boot your machine, the machine will go out to the DHCP server and it'll say, I need an IP address. This is who I am. This is, my Ethernet card and the like. And it will, the DHCP server will give you what's called a lease on an IP address. And that lease is valid for a certain number of days or hours, or usually it's valid for 2 weeks. And then it has to be renewed, and it could give you a different one or the same one. In practice, if you don't have a very dynamic network, which we don't, you typically always get the same IP address when you renew, and so your IP address is stable over time. I think I've had the same one on Media One for years. And certainly, over the course of the project that you will do, hopefully all of your IP addresses will remain static. So when you're talking to each other's machines, you will always be talking to each other's machines. Unfortunately, we don't have any DNS server running on for your machines. So your machines do not have any domain names. Maybe we'll try and set that up. Probably it's a little too much of a hassle. So your all machines are called like localdomain.localhost or something, or localhost.localdomain. So we'll have to communicate through IP addresses. Yes?
You can distribute a host file.
Ah, that's true.
We already have like a quick way to.
That's true, and we all have, that's a good thought. So we could give you all machine names, which I think would be much more mnemonic than those. But we need to know those, and so one thing I would like you to do is there is well, I'll wait till the end of class.
By the way, what does DHCP stand for?
Host configuration program.
Thank you. Thank you. Sometimes you get lost in the acronyms. There's all sorts of protocols that support this. There's an like ARC and then an RARC, and but each one of these protocols, if you want to know about them, has not only a standard port, but these are all defined on the internet, and they're usually defined in a document called RFC, for request for comment. In the early days of the internet, these were basically made up by people who wrote a piece of software that did this sort of thing and wanted to share it with everybody, and they wanted other people to be able to hook into it, so they published these protocols in these RFC documents and just put them out so people could read them. Nowadays, of course, there's big international standards committees that are pretty much doing the same thing. RFC stands for Request for Comment. One thing we haven't talked about, let's see, there's a piece of code in your notes, which unfortunately can't run today, that will open up a connection to port 80, the HTTP port, and do a simple HTTP command. HTTP is another text-based protocol, and the command for just getting a file for download is particularly simple. You just have to write get, and then the path name, the thing that follows this in your URL. Okay, so get/path. Yes, all capitals get. And then a space, then the path, then a space, then HTTP and whatever version you're pretending to be. So 1./1.0 will probably work. And then \n, meaning exactly 2 carriage returns at the end of that. Okay? So if we dump this string, so what this URL means is open a socket on this host name and this port, and then do a get with this path. Just take the rest of this string, put it here, embed it in here, send that message off. If you do this in Java, on Stream.io, you must do a flush, I've discovered. Otherwise, only part of it gets over and the connection times out. So make sure you flush your network connections after every message. And then read stuff on the socket. And the thing you'll just do read lines, and what will come back on that socket is the HTTP, or the HTML rather, for that page. So if I did get slash, if I just did slash on arsdigita.com port 80, I would get the home page of Ars Digita. And granted, you know, it would be in raw HTML. You'd see all the angle brackets. You wouldn't have it nicely displayed, but that's what that little program does.
Now, if it happened to be on a machine running Windows, would you have to do the slashes, Windows-style slashes, or does it automatically correct?
Good point. The URLs, okay, the definition of URLs, including path parts, is yet another network protocol standard, and it has another RFC. And the RFC specifies that everything has to work with forward slashes. It might say that things can work with reverse slashes as well. Java has some facilities for setting the path specifier, I think, but the path name separator. But the specification for path names in URLs since it is a network protocol, has to be specified independent of any particular machine architecture. So to figure out how things are supposed to work, you can go to the URL RFC, and it will also tell you all sorts of things like how is relative file name resolution supposed to work, and how, if you in HTML you can specify a partial path name. Okay, you can specify just some ending of this, and the system will automatically concatenate some beginning part, which it thinks is correct, and it will tell you all the rules to this. Okay. You do not want to implement all of the rules for that, and the process of taking apart and dealing with URLs is a sufficient hassle that Java has given you URL connection classes that particularly handle HTTP, the HTTP protocol, the URL protocol, and even some classes that will handle HTML. So if you look at the end of the network book, the network chapter in volume 2, you'll see a bunch of classes that talk about URLs and URL connections, HTTP connections. So they're just utility classes. They essentially work the same, except they know about HTTP and the commands you can send. So if you were really doing a web server, you would, or some web application, you would want to use those classes, most likely. Okay, one thing we have not talked about, we talked about how to connect as a client. We have not talked about in Java how to be a server. So I think I'm going to erase the brain for that so everybody can see. This is, again, way simple. There is another class called server socket. I'll call it SS equals new server socket, and then you just give it an integer, which is what port you want to listen on. All right. So as I said, the server wants to start up something that listens for incoming connections on this socket, and this is the thing you create is server socket. And this doesn't. Now you need a way to, when somebody actually connects to you, get that connection and do something with it. So the magic method on server socket is called accept socket s equals ss dot accept. Okay? And what accept will do when you call it is block on that port. Okay? This code will just sit there in the lower levels of the network system, waiting for somebody to connect to you. Okay? And as soon as somebody does connect to you, it will do this business of taking the end of the socket that they're trying to create, creating a socket on your side that corresponds to the stream on their side, and return to you this. So it's going to make a socket object, which is different than your server socket object, and return it to you. Okay? And now once you have this on the server end, you now then get your input stream, your output stream, and you're ready to talk to the client via whatever protocol that you've agreed on to talk about, sending bytes or text or whatever. One twist on this is that once you do an accept, this thread is continuing to execute. He's no longer blocked, and there's nobody here that's going to accept the next guy who tries to connect. Right? The only way you can get a connection is if you have some thread in the accept running accept. Okay? So if you only want to handle one client at a time, you could just make one of these and then run a loop that they called accept, and then did serviced one client, closed the connection, and then went back and waited for a new connection. If you want to accept multiple people, if you want to handle multiple servers, what you have to do is every time you get an accept, you need to fork off a new thread to handle this connection. So, and you give it this socket, and then this guy just goes back and waits for somebody else to connect. So you have one thread that's basically in this accept loop, just waiting for people to connect to you. And then as they come in and connect to you, you're kind of spawning off threads saying, here, deal with this guy, deal with this guy, deal with this guy, deal with this guy. Okay, it's one of the reasons we did the thread lecture before the network lecture, because you need to, if you're running a server and you want to serve a variety of clients, you basically need to be able to spawn off threads, server threads, that will perform the function. These are all running the same kind of server side of the code, but they're all running in parallel now, because you could have, tens or hundreds, or in the case of a web server, thousands of people connecting to you. But that's all the calls you need to know for the network stuff. Yes?
At what point are you referring to a physical entity? Like the socket's an object, and you're talking about getting access to a program?
Right.
The president of the program, is it the port? Is that?
Nope. The only physical entries in this whole thing are way down here. Okay, everything else is a software abstraction built on top of. The only physical entities in this whole thing that you can touch are the network card in your machine, and then the wire coming out of your machine, or the wireless coming out of your machine, and the corresponding connection on the other side, and then you could trace that physical connection through the world. But everything on top is mythological. It's entirely abstractions created by massive amounts of software, layer after layer after layer.
So port is an addressing scheme, just like IP is an addressing
Right.
scheme. And
It's just something that people agreed to. There's no, like, if you look at the back of a computer, there's no, like, ports. It's entirely an agreed upon scheme between people, implemented by that layer.
Does server socket have a method you override that actually then gets the connection when a connection happens? Is that the way?
No, it's this accept thing is the thing that gets the connection.
And
that returns you a socket. And that socket you can do reads and writes on.
How do you know the IP numbers are unique when they send them? Is there a huge database that you check?
Well, there are rules to assigning the IP addresses to make the routing work. And essentially, at the beginning of time, the namespace was sliced up. Okay? And some small number of people, so each, this namespace is divided by rule among various organizations in the world. There are a small number of people who are around at the beginning of the ARPANET who have namespaces that only fix this number, and so have a namespace that is huge in that it's 24 bits worth of IP addresses. Okay? MIT has one of these called Class A namespaces. Digital Equipment has a Class A namespace, which I think starts with 16. Does anybody know MIT's? Compaq, right. I used to work there, so I should know. That's one of the things Compaq got when they bought Digital, is this beautiful Class A namespace. BMW has a Class A namespace? Really? Wow. A lot of universities and the government have one of these. Then there's some of these high digits that are restricted to what's called Class B, which fix these two numbers. And of course, there are more of those, but each one is smaller because it only has, you can only vary that bit. And then some people have these smaller namespaces that only have 256. So these are like divvied up around the world. And then there's a lot of cheating going on because, the way these divvy up is not necessarily, the way these machines like Ars Digit alone could probably fill up an entire one of these things. and we probably have more machines than that. So what you do is kind of behind various layers of gateway, you assign local IP addresses, which then get kind of funneled into real IP addresses and then expanded back out. So there's lots of games you can play. But at the lowest level, if either DHCP screws up or your network administrator screws up, and on your local network assigns two machines with the same address, very bad things, very confusing things will happen, because packets will go all over the place, and machines won't know what to do, and they'll be talking to each other. And I once gave a talk at a conference where they were using some DHCP-like thing that wasn't working very well, and people would come up and give their talks and try and demonstrate their websites. And then the next speaker would get up and connect into the same thing, and sometimes the DHCP was not functioning properly. They weren't getting unique IP addresses, so you were getting somebody else's demo on your machine, or your demo wasn't working, and it was unfortunate. But things are better now. Last thing, the internet address class. Java has some utilities, a class called INETAddr, or INETAddress, which just has a bunch of nice routines on it for manipulating internet addresses. They can take host names and do the lookup, or turn these things from text to binary to string to whatever. And then one thing that's good is there's static methods on here that will let you read the host name and IP address of your machine. There's also a Unix command that'll print that out called ifconfig, right? It's something, yeah, ifconfig under Linux. One word, and it'll type out a bunch of data. So what I need from you for problem set 3, so we can get our infrastructure organized, is if everybody would either run the program that's in the back of your notes, which basically uses this to detect your IP and host name, or run ifconfig and print out on a piece of paper your name and IP address of the machine you're working on. That way we can set up some kind of host name naming scheme, or just know when we try and connect to each other what namespace we have to work with.
If you want to put a name for your computer too, we'll set up a host file. So think of something fun.
Okay, so yeah, on that piece of paper also, if you don't want your email address, which will be the default name, yeah, come up with something not too fun, but but reasonably fun. Okay, that's it.